How do we map neuromorphic concepts into chips built from silicon? Here's Mike Davies, Senior Principal Engineer and Director of Intel's Neuromorphic Computing Lab. This is Architecture All Access.
Let's now talk about how to architect a chip that behaves more like a brain than the chips we're familiar with today. If we step back and look at the state of modern neuroscience and chip design, we see that we can clearly build CMOS circuits that replicate some of the form and functions of biological neural networks. People have been experimenting with this for over 3 decades. But an approach of directly copying the structure and circuit dynamics of biological neurons quickly runs into practical trouble. The design tools and manufacturing technology we're working with are simply too different from biology's. Specifically, in terms of transistor area and wiring resources, we are many orders of magnitude behind what evolution has achieved with its DNA-based molecular 3D self-assembly techniques. As a chip designer, I'd love to get my hands on nature's circuit design toolbox, but those capabilities are going to be a very long time to come. On the other hand, today's CMOS semiconductor manufacturing technology does give us some important advantages. In speed, for example, we can construct extraordinarily fast circuits compared to biological neural circuits. While biology operates at milliseconds and kilohertz scales, our CMOS circuits operate at nanoseconds and gigahertz. And we can construct reliable circuits that operate precisely and deterministically, whereas in the brain, precision and reliability come at the expense of redundancy or more neural resources. So this leads us away from the idea of literally copying or exactly replicating the neural structures we find in the brain. Instead, we have to understand and adapt the underlying principles of brain computation to the design toolbox we're working with. But despite the different design tools, the same principles surely apply, since we're targeting the same objectives: intelligently process sensory input quickly while minimizing both energy consumption and manufacturing cost. So let's consider some of these principles. One of the most fundamental is the virtue of sparse, distributed, asynchronous communication. Consider the problem of communicating the activations of a set of neurons to some downstream neuron. If somehow only the most strongly activated neurons could asynchronously announce themselves in time, then the most important inputs can be processed quickly with minimal latency. On the other hand, if the entire set of input neurons has to be processed as one dense matrix, which is the standard way in today's mainstream architectures, then the important inputs will get congested and delayed behind the herd of less important inputs. This may seem obvious, but to truly exploit this principle, a hardware implementation needs to respond to unpredictable neuron activations immediately, which implies extremely fine-grained parallelism and neurons that asynchronously represent their activations as events in time rather than as numbers in a synchronously processed vector. This is what biological neurons do using spikes, and it's what we aim to implement in neuromorphic chips. Now, if we turn to the problem of routing those spikes in a chip we can build, we're going to find a clear example where we can't just copy biology. Brains use truly three-dimensional routing with tens of thousands of overlapping wires through any cross-section. In contrast, our chips, vertically, we can only stack about 20 metal layers. This is a huge wiring disadvantage. But remember, we have an enormous speed advantage. So what we can do is packetize the spikes and send them over shared time-multiplexed horizontal wiring channels, giving us effectively many more vertical layers. The packets can then be distributed over a routed mesh network at speeds of up to 1,000,000 times faster than what biology uses for its spikes. At those speeds, the routers can distribute thousands of spikes over the same wires in biological timescales without interference, as if each neuron had its own dedicated axon wiring network, as in the brain. Now you may think this looks incredibly inefficient. Spikes sent as packets with 32 or more bits sent over bundles of wires? How could this possibly reach the level of efficiency and density in the brain? But actually, we're not that far off. The brain's long-distance wires are myelinated axons, which have a diameter of about 1 micron. In modern semiconductor process technology, we can easily pack all the metal we need in a 1-micron strip of planar wires. So our brain-inspired spiking interconnect is in the ballpark of biology. And once we have these routers, we can now connect them to neuromorphic cores that produce and consume these spikes by modeling the essential behaviors of biology's temporal spike-based neurons. Each core needs to continue to time multiplex its circuitry so it can reduce its effective area per neuron by orders of magnitude. This way, each core, with a fraction of a square millimeter, can implement several thousand neurons, which actually approaches the neural density of the neocortex. By implementing spike-based neuron models, the activity and communication levels are far lower than what you'd have in a conventional chip. The cores send their spikes as sparse peer-to-peer distributions, leaving the routing network relatively idle compared to the buses in a conventional chip. In this architecture, there's no off-chip memory interface that has to stay saturated with predictable vectorized memory patterns. This all translates to lower power. Now moving on to a real neuromorphic chip, here we have Loihi 2, developed by my group and one of the most recently developed neuromorphic chips. The chip plot, frankly, looks rather boring because, like a memory chip, it's mostly a single repeated core instantiated in a mesh, and the core is itself dominated by internal memory structures. Loihi 2 is a fully digital chip implemented in a standard CMOS process. Historically, many neuromorphic research chips have used analog circuits to replicate the membrane dynamics of biological neurons. But for many reasons, relating to circuit density, precision, reliability, the field has generally moved to fully digital designs, at least for now. The brain is one massive asynchronous circuit, and a lot of neuromorphic chips, including our Loihi chips, are implemented using an asynchronous design style. Asynchronous circuits don't use free-running clocks and automatically stop consuming power when there's nothing to compute. Of course, this is a great match for spiking neural networks that are only sparsely active. If we now dive a bit deeper into the details of Loihi 2's neuromorphic core, you'll find an asynchronous signal processing pipeline with a lot of internal memory. Memory is the scarcest resource in a neuromorphic chip, and unlike compute circuitry, its effective area cannot be reduced using time multiplexing. So the rest of the core circuitry is highly optimized to use this fixed pool of memory as efficiently as possible. For example, convolutional features allow a repeated pattern of synaptic weights to be stored only once and then reused across multiple neurons. The core's memory is a granular array of many banks with varying sizes. Different processes in the core require different levels of access parallelism. The memory can be allocated in a flexible way across the core's pipeline stages, although the performance and storage density are optimized for the typical configurations. As spikes arrive at the core, table lookups determine what neurons in the core the spikes connect to. The lookups return data structures that specify weights and propagation delays for each destination neuron. As each spike is applied to its fan-out neurons, the associated weights are absorbed by a dendritic accumulation process, which maintains the total received synaptic stimulation for each of the core's neurons. In a completely decoupled asynchronous process, the dendrite stage reads each neuron's accumulated synaptic input and then updates the neuron's state variables for the current time, following the neuron's programmed model. Typically, synaptic input causes a neuron's state variable to jump in a positive or negative direction, while the absence of input causes a gradual decay of the variable to zero. If a neuron becomes sufficiently activated and crosses a threshold, then it generates an output spike. Further table lookups in an egress process determine which cores in the network the spiking neuron connects to, and then spike packets are sent through the routing infrastructure to those destination cores. In Loihi, we also have a learning process that operates in the background, updating the parameters of the core's neural network, particularly the synaptic state variables. Based on a combination of the input side activity and the output side activity at each synapse, its state variables, such as its weight, can evolve over time according to programmed equations. Getting these so-called learning rules right so that the large-scale behavior of the network is to adapt online and usefully learn new patterns is one of the trickiest and most actively researched areas of neuromorphic computing. And that concludes our quick tour of neuromorphic architecture. Hopefully, I've provided an understandable glimpse into the world of neuromorphic computing, and you're leaving with a greater appreciation for this rather different and exotic architecture. The architecture is actually the relatively easy part. We can build these chips today that support many of the computational principles we find in brains. But understanding how to program them to perform useful computation, that's still admittedly a formidable challenge. The field is making a lot of progress on that, though, with some exciting results. For example, in the domain of optimization, Loihi can solve problems like railway scheduling and QUBO from quantum computing with orders of magnitude gains compared to the best conventional solvers. So please check out some of our recent publications and follow our progress as we get this technology out of the lab and into game-changing products. This has been Architecture All Access Neuromorphic Computing. Thanks for joining us.